In previous videos of this unit, we have just ignored situations where we didn't have a linear pattern in our scatter plot. But today's the day we're not going to ignore those non-linear patterns anymore. We are going to figure out how to make them linear. Yeah, that's not super uplifting. We're going to force all the non-linear stuff to be linear. We're just going with it, okay? Turns out there are ways to take non-linear data sets and make them linear so that you can use all the tools that you've learned about in this unit to analyze the data. So, the nice thing about this activity is you could probably do the entire thing without my help at all. In fact, the summaries on the last page are fully written out. So what I'm going to do is give you a couple hints. I'm going to have you pause the video, and then you're going to do as much as you can, and then come back to the video just to recap things with me. So first of all, the hints. There is a Google spreadsheet here with the data. As we've done in the past, you're going to want to make a copy of this, so click on File and then make a copy. That way you can edit it. And just as a reminder, if you have to type in a formula, the formulas always start with the equal sign, and when you hit enter, it'll compute. If you want to drag that formula to more cells, you have to click this little box in the lower right-hand corner and you drag. Oops. So, just a heads up. And then to get things into Statlet, you can just copy. I'm just doing Command C, and then V. One other hint before you get started. Everything in this activity is Y versus X. So this first example is income versus mortality rate. Income is the Y variable, mortality rate is the X variable. One way you can think of this is income as a function of mortality rate, right? Like Y as a function of X. Anytime you see anything in this activity that's blank versus blank, it's always Y versus X. Okay, what you should do is pause the video and do as much as you can before you need to recap. If you do the first page and you're feeling great, just keep going. If you do the first page and you want to check with me and make sure you're doing things right, hit play and just watch the first page explanation. No matter what, you should just watch the recap with me at some point. It's just up to you when you do that. So our first example definitely wasn't linear. I drew in the shape here. It was definitely more of a 1 over x shape. These points up here make it not very linear at all. And we can tell it's not linear because r squared is 0.337. So that line is not doing a very good job of predicting values. And the standard deviation of the residuals is also enormous. Okay. So then we changed x into 1 over x, and that looks much better, much more linear. Now the slope is positive, which is interesting. And notice in my equation, I've written 1 over mortality rate. Okay, so you have to note in your equation that you changed something. It's not the right equation if we just do x. It has to be 1 over x. You can see right away that this line is much better because r squared is higher. This is much closer to 1 than 0.33, and our standard deviation of the residuals got much smaller. And then holy cow, on this last one, the picture didn't save for some reason, but in this last one we put x back to normal, and now we're changing y to 1 over y. Look at r squared, even closer to 1. Now it's in the 0.9s, and the standard deviation of the residuals, I think due to rounding, Statlet just told me it was 0, which is pretty small. Notice once again in the equation, it's back to mortality rate, and this is 1 over income. So x is the original, x is normal, and then y is 1 over y. In this example, we're just plugging values into each equation. So you'll notice in the example that was done for you, it's 1 over the value they want you to find, so 1 over 30, and then it's just typing things into your calculator. For part D, we're plugging in 30 over here. This is all typing things into the calculator. And then what I did here was I multiplied both sides by x. I guess technically we're solving for y. I should have made that y. And then divide by the 0.000234. Okay, so we get 4,273.5. And yes, those two values are different. And we would get a third different value if we used this not so good predictor up here. Each line is giving you a slightly different prediction for a mortality rate of 30. Based on the r squared and the s values, I would say we'd want to go with this line, our third option, just because that had the r squared closest to 1 and very small residuals. Okay, in the second example, we're comparing the length of fish to their weights. So the original, definitely not linear. We have this curved shape, although look at R². Like, that's pretty good. And you can see it on the graph. Like, we could draw it in a line, and it would be okay. It would be okay. But we can do better. So since weight is a three-dimensional measurement, there's a typo that's fixed on yours, we're just going to do x cubed. When we do that, we get something that is much more linear. So here's our new equation, length cubed. Notice in the equation I wrote length cubed. R² is much closer to 1, standard deviation of the residuals much smaller. So that one worked very well. And then the last thing we did was changed weight to cube root of weight, which if you think about weight being a 3D measurement, if I cube root it, it's going to get to a 1D measurement. So that's why we did that. Notice that length has gone back to normal, and now weight is cube rooted, or raised to the 1/3. Those are the same thing. And R has improved. We're closer to 1, and look at standard deviation of the residuals, even smaller. Like, you were impressed by 18. Look at that. That's good. All right, so here in our two examples, in part C, you'd have to do 20 cubed because we're cubing the length. And in part D, this over here is all just typing things into the calculator. And then if I want to get rid of this raised to the 1/3, I cube both sides. So I got this number by cubing the 4.90996. Okay, last example. This is a real activity that I do when I teach Algebra 2 when we do exponential growth and decay. In the original, here's our equation, .811, standard deviation 5.33. And just like the last example, it's not bad. Like 0.811, that's fine. But this is an example of exponential decay. So I think we can do better. Now, exponential decay looks like this. We have something raised to the x, and it's okay if you don't remember this from Algebra 2, but to undo raising something to the x, we have to take the log to get that x out of the exponent. So what we're going to do is first take the log of y, and that gives us something that's much more linear. We get an r value much closer to 1, standard deviation of the residual is much smaller. And then just for fun, we can take natural log of y. You'll notice for this one that R² is exactly the same, but the standard deviation is a bit different. That's just because natural log is base e and log is base 10. We have a slightly different scale for the y-axis, but the x-axis is staying the same. So these scatter plots are essentially exactly the same, it's just the scales of the y-axis are different, which means r and R² stay exactly the same. Okay, and then finally at the end here, just to review if you haven't solved logs in a while, you first want to simplify all of this into just a single number, and then your teacher might have taught you to do this like jelly bean shape or kidney bean shape, or some teachers call it a scorpion tail, a variety of shapes, but what you do is take the base of the log raised to this number equals this number. So 10 to the 0.71 equals M&Ms. That's here, 5.13. And exact same thing over here for natural log, except natural log is base e. So that's e to the this number equals that number. Okay, so here's our summary. When the model looked like a reciprocal, we took the reciprocal of x or y, and that made it linear. When we had a theory that suggested that y equaled x to the third, we cubed x, or we cube rooted y, and that made it more linear. When we had a theory that suggested the model was y equals b to the x, we took the log of y, and that made it more linear. Now those all worked because we had theories. We knew that one was exponential decay, we had a theory about length versus weight, but let's think more about number 2. That was a really specific example about fish. I'm not sure how often you're going to be making a scatter plot about fish. I'm guessing not very often. Instead of thinking about x to the third, maybe we just think about it as x to any number. Call it p for power. That type of model is called a power model. And there is a way to deal with any power model, whether it's x², x cubed, x to the 10th, x to the 100th, anything. The key is to take the log of both sides, not just x, not just y, but both x and y. So here I have log of length and log of weight. You can see this is a really impressive linear pattern. Like that looks like connect the dots. And the r squared value was the closest we've been to 1 this entire activity. Standard deviation of the residual is also really small. So how does it compare? It's the best. R squared has been the closest to 1, and look at that scatter plot. So this is the fourth part of the summary. If anything looks like a power model, you can take log or natural log of both x and y. That means if something looks like x squared, or x cubed, or x to the fourth, or x to the fifth, etc. So when it comes to linearizing data, first you need to remember the different strategies or theories that you can use to linearize. The first thing would be if there's something obvious like the weight example. The length compared to weight, if you cube the length, you're going to get something closer to weight. That had a really specific theory, and if you're presented with a really specific theory, go with that. But if you don't have a specific theory, there's a couple different scenarios you could try. If it looks like it's 1 over x, use the reciprocal theory. If it looks like it's exponential growth or decay, use the exponential theory. And if it looks like it's a power model, like x squared, x cubed, x to the fourth, x to the fifth, etc., use the power model. Once you've determined which one to use, you do have to be able to remember what you're supposed to do. So if you notice that it looks like it's reciprocal, you have to remember, oh yeah, that means I do 1 over x or 1 over y. If you notice that it looks like it's a power model, you have to remember, oh, that means I take the log of both x and y. If you notice that it looks like exponential growth or decay, oh, that means I take log of y. So there's kind of 2 steps, if you can see that. There's the first step of which theory should I use, and then there's the second step of what's that theory again? I highly recommend that you make some kind of graphic organizer to keep these straight, because it is a lot to keep track of. But in the end, linearizing any nonlinear data opens up all of the tools that we've learned in this unit so that you can actually analyze it. So even though it is kind of challenging to keep track of all these different theories, it does make it so that we can analyze data, and that's awesome.